Okay, so this presentation is called Fixed Point Made Easy. My name is Jeff Miller. I've been an application engineer at the MathWorks for about 15 years now. And the idea of this presentation was to pull together a lot of the knowledge that's been learned from doing, for myself, projects taking algorithmic MATLAB code, floating point in particular, to fixed point implementation that will do well on FPGAs. And the idea was to kind of bring together the different domains that come into play. So understanding of the theory of fixed point mathematics, hardware architecture, and FPGA implementation concepts, and then how to express those together in MathWorks tools. And if you can kind of pull all that knowledge together, you can do really, really well taking a floating point design all the way to implementation fixed point on an FPGA. And the technical agenda for today, for this talk, is we'll go into the fixed point theory. We'll review the number system, what it means to be full precision. We'll take a look at some mathematical ranges on addition and multiplication. We'll go through some common functions. We'll focus on square root, reciprocal, and log 2 are really all of roughly the same kind in terms of how you would attack building them fixed point. We'll focus on reciprocal, but we'll make available examples and readmes for the other two. Similarly, from the trigonometric functions, we'll go in a little bit more depth on cosine, sine, and then make an example of arctan2 available. For the higher level IP functions, we'll talk a little bit about FIR and FFT. We'll go through some of the concepts you have to have in mind as you're going to an FPGA, and then we'll actually conclude with an FIR filter example and a methodology. So let's start with a quick review of fixed point theory. What I've done here on these next couple slides is take a look at what it means to be full precision. So full precision is kind of how large a result you need in order to be able to fully represent without any quantization issues. So what we can see is the actual same rule holds for base 10 or binary. So if you had a 4-digit base 10 number, in the diabolical case, if you take the largest two ones and add them together, what you can see is you grow by 1 digit. And the same thing happens in binary. You would grow 1 bit. Okay. Now, if you were to look at that for multiplication, what you would see is that the word length actually doubles. Okay, so we have this notion of grow 1 digit on an add and double the word length on a multiply. And I'd like to get into just a quick example of how MathWorks notation works for fixed point numbers. So I'm actually going to open up MATLAB here. And we'll do x equals 5. This is for fixed point of 0.44725, comma 1 is we're going to do a signed number. 18 is the word length. We'll see a little bit later, 18 is a great choice for word length, and 16 is fraction length. Okay. And what I want to know is how do I go back and forth between the two? And there's this notion of stored integer you'll see in some of our documentation. The idea is that ultimately under the hood in hardware, there's really no actual physical binary point. There's just raw ones and zeros. There's just an integer itself. And you can actually get that value simply by doing int of x. Okay. And if you want to go back from this stored integer value of 29,311 back to 0.4473, then you can just simply do this, the stored integer, times, in this case, 2 to the minus fraction length. Okay. And that would get us back to what we would call the real world value. The other thing to kind of be aware of is that there's kind of a natural range that you can represent for any fixed point word length and fraction length. And if you go back and review 2's complement arithmetic and notation, what you'll see is you can always go a little bit further in the negative than you can in the positive. That's because 0 is actually treated as a positive number in 2's complement, so it chews up one of the values. So if you wanted to just quickly say, put in something you know it can't quite represent, if you put in like 100, okay, you can see, and we'll do a format long, that you can go to not quite 2, Okay, and if you went for the negative and try to go beyond the rails, you can actually go all the way out to -2. Okay. And let's go back to the main presentation here. So this is just a summary of what we just did in MATLAB. As I said, an 18-bit word length, we'll talk a little bit later, that's a natural word length to choose for an FPGA, be it Xilinx or Intel Altera. 16 fraction length enables you to represent -2 to not quite 2. I tend to default to this setting a lot. If you're computing cosines and sines, then your range is -1 to +1. If you did an 1817, you wouldn't be able to fully represent the +1. So this gives you a little bit of headroom. Okay. Now, just deriving from a theoretical standpoint, how much error you expect for a given fraction length. If you were to do a round to floor, then you could, in your partition was fraction length, and we'll call that delta equals 2 to the minus fraction length. Well, then your maximum error is effectively delta. You could always be flooring the whole thing. Okay. If you took an average value of the error, and we don't have to do the full calculus here, it would be on average your error would be delta over 2. And the fact that you do have an average value of the error here, even with uniform distribution, means there is a bias to when you round to floor, because you're always losing a certain amount. The main thing here with the root mean square and the signal to noise ratio is that's where you start to get this concept that a lot of people have as a rule of thumb, which is that you get 6 dB per bit. So that if you think in terms of a noise floor in the frequency domain in particular, every time you add one more bit of resolution, you can see the noise floor actually improve by on the order of 6 decibels per bit. Okay. If we do the same derivations using round around the nearest, well, now the maximum error is going to be cut in half, because at the halfway point, we would actually start rounding in the other direction. If you were to average the error over the interval, half of it would be negative, half of it would be positive. The average value would be 0. We still have this concept of 6 decibels per bit. So what I did here is I just kind of put those results in a table. And what I'd like to do now, one of the things we really wanted to focus on doing today was understanding something from a theoretical standpoint, and also understanding how to express it in MathWorks tools, and making sure we're reconciling them and that what we see in one matches what we predicted in the other. Okay. So what I'll do here is I'll open up a model where we're actually going to quantize to 6 bits. Okay. We're just going to use some sort of random source. And we'll take the quantized value and we'll actually subtract that from the known right answer. And we'll do it once when we did a round to floor and once when we did a round to nearest. And over here, what I've done is written the predicted values based on the theoretical derivations from the last slide. And we'll go ahead and give that a run. And what we can see here is that if I look at any of them, they're pretty much on par. We predicted 7.8125 here for the average value with the floor, pretty much spot on. We're getting 10 to the minus 6 when we did a round to nearest. Again, looking at the maximum errors, very consistent. The running root mean squares. Everything's pretty much on par with the theory. Okay. And now what I want to do is take a look at this in the frequency domain. And we'll open that up here. And what I did in the frequency domain is I did one where I did a round to floor, and I want to point something out there. And then I did 3 in parallel where I did 12 bits, 6 bits, 16 bits, and 20 bits. And we'll look at those spectrums, okay? So we'll give this a quick run. And what I wanted to point out here was in the case where we did a round to floor, when you look at the spectrum, what we were actually doing is we were sending in a sine wave, okay? And when we do a round to floor, what you'll see is you actually pick up a small spike or DC bias. That's because we're always rounding to floor. That's why we actually see a little bit of a DC component here. Now, when I looked at the case for 12, 16, and 20 bits of quantizing to that much resolution, what you'll see here with 12 bits, we're on the order of minus 70 for the noise floor. We would expect, using the rule of thumb of 6 dB per bit, if we go from 12 to 16, we would expect an improvement of about 24 decibels in noise floor. So you can see we're going from about minus 70 down about minus 95, 94. That's consistent. If we add 4 more bits, we should be down another 24. So that should be on the order of maybe about minus 118, minus 120. So that's consistent. So that we're seeing in the frequency domain as well consistent results on the order of 6 dB per bit. Okay. And we've got a couple background slides on some of the rounding modes and how that kind of maps back to what implements in hardware, and just to kind of review MathWorks definition for things like convergent rounding, nearest rounding, and so on. So we have a table here of results. I'm not going to go through every entry. There's a link to that in the slide as well. They do have a little bit of implications when you go to generate VHDL Verilog. You can see why the nearest is kind of the more natural of the 3 to build, besides, of course, floor. And in the prior table, it also talks a little bit about the bias and the complexity of hardware implementation as well. So what I'd like to do now is go through this class of functions, which is reciprocal, square root, log 2. We're going to make available some custom implementations of those. They have some nice properties. One of the tips and techniques for building these, and they were all done, all 3 of these were done with lookup tables, is that the lookup tables will do really well if it's operating on a number between a half and 1. So if you can, by shift arithmetic, which is effectively multiplying by powers of 2, scale the input so you're in between 1/2 and 1. Do a lookup table with linear interpolation, and then correct back by the powers of 2. Okay, so what we'll do here is we'll take a look at that applied to reciprocal. And here I have a MATLAB test bench. Okay, that's actually going to drive a Simulink model that's doing reciprocal. Okay, we're seeing that the maximum percent error is on the order of 3.6 times 10 to the minus 3. That's for percent error. And what I'll do is I'll just take a quick look at the model and highlight a few things. The first thing here is the normalizer. This is what makes sure the input is between 1/2 and 1. And one of the things that can get you in trouble with fixed point is what's called sine extension, where you come in with a lot of leading zeros. So and that's effectively coming in with a value much below 1/2. So what this does, it can be referred to as a barrel shifter, is it tests the upper 16 bits of the input. And if those are all 0, then it's going to left shift by 16. Okay, and then it advances if the next 8 bits are, if after that 8 bits, the leading 8 bits are all 0, then it will left shift, and so on. And if you do that through these stages here, by the time you're done, you would actually have a number that has to be between 1/2 and 1, okay? And from that, we actually go to a lookup table that's doing 1 over x. And you can use the lookup table to give you 1 over x, and then also the difference between that entry and the next entry. And if you go to the linear interpolation formula, the value that you compute comes from the initial value from the lookup table plus delta, which is these lower bits that you extract, times the final minus initial entries in the lookup table, which was actually put in here. So now we're doing our linear interpolation. We're looking up 1 over x, and then we're also multiplying by the delta, okay? and that computed value gives us a nice accurate result. And that's kind of one of the techniques you can use to get floating point level accuracy for fixed point functions. We also have a library that just does it directly with floating point HDL. And I do want to kind of just provide the caveat that you want to use these when you need the high performance in terms of mathematical accuracy, but you don't necessarily want to use them to replace every single function. For example, you wouldn't necessarily want to do an FIR or an FFT with floating point functions. One of the reasons is they do add a bit more area and can take more clock cycles to work through. Just to do an accumulator, if you were trying to do that floating point, you can run into a little bit of the awkwardness that the addition can't be done in one clock cycle, and that can add a little bit more complexity than that's really needed. So we tend to encourage the use of floating point HDL when you need a really high accurate formula, not just to completely replace fixed point. But it is some nice functionality to be aware of. I didn't want to talk about the trigonometric functions. So the two ones I highlighted, and I also wanted, there are a few different instances of them in the Simulink libraries. I did want to highlight kind of the recommended ones for arctan2 and sine cosine. For arctan2, I recommend using the complex to magnitude angle block. For cosine sine, I think the NCO block does a really good job. And I also want to show an example of building cosine sine from scratch for a couple reasons. One, that example kind of shows a nice way to get a really high degree of accuracy, and it also teaches this concept of doing things mod 2 pi and getting the scaling right to leverage that. So let me show that example. So here what we did is we actually computed e to the j omega naught n for a particular frequency. And we built an NCO from scratch. And what I want to highlight is a couple things. When we accumulate an angle here, we come in with an 18-bit number, and we're going to accumulate the angle, and we're always only going to extract the lower 18 bits as we accumulate a theta. And the way we think of it is we think of 2 to the 18th as really mapping to 2 pi. And that really helps out a lot with your angle arithmetic, because if 2 to the 18th corresponds to 2 pi, then when you keep the lower 18 bits, you're effectively doing mod 2 pi. So that just kind of comes naturally. You don't have to compare anything to 3.14 times 2. You just extract the lower 18 bits, and that does your mod 2 pi. The other nice thing about this particular example here is it does use kind of a 2 lookup table technique to get a real high degree of accuracy. So for example, if you're trying to compute cosine sine of an 18-bit angle, instead of using like a 12-bit lookup table and trying to do dither, what you can do is have really just 2 9-bit lookup tables. And so one 9-bit lookup table would represent the upper 9 bits, and a 9-bit lookup table would represent the lower 9 bits. And if you then do a complex multiply between those two, well, then the angles would add, and that would represent the entire e to the j theta. Okay, so you now have the accuracy of an 18-bit lookup table while only using 2 9-bit lookup tables. Okay, so you can see here we extracted the upper 9 bits, here we extracted the lower 9 bits. There's 2 different lookup tables and then a complex multiply. And if you look at the mathematical performance, the error was on the order of 10 to the minus 5. If we actually look at the spectrum here, you can see that the noise floor is actually over 100 decibels down, because this is north of 20 and this is below 80. So the noise floor in this case is actually over 100 decibels down. Okay. And the last thing I wanted to review for the high-level functions was to take a look at FIR and FFT. And if you go to the formal definition of FFT, which I've shown from our documentation right here, if you look at it carefully, what you'll see is that IFFT actually has a 1 over n, where n is the length of the FFT, IFFT built into it. Okay, and that means from a scaling standpoint, the IFFT is a bit more better behaved. And FFT would actually scale the signal. You would come out larger than you came in. Okay, so you do have to be careful that FFT has a log 2 of n growth, and the diabolical worst case input for an FFT. And so from an HDL standpoint, you'll actually see we have a checkbox there which says divide the butterfly outputs by 2, and that would actually keep the maximum value the same coming out of the FFT as what came into the FFT. Okay, so that's a popular checkbox to do. Just wanted to provide a background on that. And what I'd like to do now is apply the different concepts we've seen here in terms of full precision, expected mathematical error, to an actual design problem. So common in wireless receivers, radar as well, this notion of using a match filter to get alignment. So for example, if you're trying to detect the presence of a wireless packet, you would match filter against the preamble and you would look for a peak. Okay, so in this particular problem here, what we're going to do is we'll have a matched filter FIR. We'll take the magnitude squared of that result, and then we'll look for peaks. Okay, and from a methodology standpoint, I'm going to set the input to an 18-bit word length. It turns out that both Xilinx and Altera naturally will do 18 by 18-bit multiplies in terms of their dedicated DSP resources. We're going to do the FIR filter full precision. We'll talk about why. We're going to quantize the output of that back to an 18-bit number. So that way, when there's the multiplications and the magnitude squared computation, those will still fit naturally into the 18 by 18 multipliers. And then we'll take a look at the quantization error to see if it's along what we would predict based off our earlier theoretical derivations. So if you take a look at the match filter here, in the problem at hand, the input is going to be a 1, 18, 16. We talked about the range on that before. In this case here, the filter coefficients are 18 bits of word length, 20 bits of fraction. If you want to do the bookkeeping there, the product of those results, you would actually add the word length and add the fraction length. So you would have a 36-bit number with 36 bits fraction. Okay. And in this example, we actually have a 128 tap filter, and the maximum growth of that would be the log 2 of 128, or 7 bits. So if you actually want to do the bookkeeping derivation, the full precision result is 4336. You could go in there and manually set that in the discrete FIR filter. If you're familiar with a little bit more tighter bounds, you can actually look at the filter coefficients themselves. And if you sum the absolute value of them, that would actually give you a slightly tighter bound. Another way to attack it would be if, for example, you're going to a Xilinx device, there's a 48-bit accumulator in the DSP48, so you could set that as your output word length as well. And just to kind of show how this might differ from C code and taking into account, for example, the Xilinx settings in particular, on a processor in C code, the data word length is going to naturally be a 16, 32, 64. In an FPGA, you can have arbitrary word lengths. You can have word lengths that aren't necessarily 16 or 32. And that has the implication, which is going back to what we had done in the theory part of this talk, is that you can use full precision a lot more for the intermediate values. So in the C code, you really have to be at 16, 16, 32, 32 on the multiplies. On the FPGA, you want to make sure you're fitting into within 25, 18 on Xilinx bit word lengths and 18 by 18 bit word lengths on Altera. So those are kind of some of the things that are driving our decision making in this process. And with that, let's take a look at this example here. So what I've done here is I have an off-the-air recording of a waveform. So we'll extract the data and then also the matched filter. Okay. Then I'm going to just make sure that the data is scaled between -1 and 1. So we have a few lines of code here to make sure that, and we give ourselves a little bit of a buffer, I think. And then we're going to order a Simulink model to run. Okay, and we'll plot and make sure the data is between -1 and 1. And I'm going to compare the MATLAB reference of the computed values back to what we got from a Simulink model that's nominally doing the same things. And I'll also take a look. We're going to have a value which is the output of the match filter, the correlator. We'll take a look at that output. We'll scale it by 1.25, which means we'll give it a range that's 25% larger than what we logged it. And we can actually quantize that to an 18-bit number and take a look at what number of fractional bits we can have and still not get overflow. So let's give that a run. Okay, and let me just show the Simulink model. So here's the FIR filter doing the matched filter. Okay, so we have an incoming waveform. In this case, you can think of from an A to D. We put it through a matched filter. Okay, and then we're going to compute the magnitude squared. Okay, so we'll square the real part. We'll square the imaginary part. And what I said here, the idea of why we call this fixed point made easy is that you really only need to make the fixed point design decision here where you're quantizing the input, and then here again where you're quantizing the output of the FIR filter. The magnitude squared part can actually be done full precision. Okay, and so with that, it came out. You're seeing errors here of 10 to the minus 15. Sometimes we call that machine error. If you do enough floating point calculations in slightly different order, you'll see error on the order of 10 to the minus 15. So that's not uncommon. Okay. The big thing here is the fraction length for the correlator out came back as 15, and we set that for a word length of 18, and we used a safety margin of 25%. Let me now run a model that actually applies that. Okay. And I'll open up that model here. And what we can see here is we can see we've quantized the input to 1816. We talked about why that makes sense before. We came in with a waveform that was -1 to 1. Here's the output of the filter, which is really full precision, 42-bit word length, 36-bit fraction length. Here is where we actually made the design decision to have 15 fraction bits. We're doing round to nearest. Okay, that's efficient hardware-wise. And now if you go into the magnitude squared computation, you can actually see here, if you look at how we take the real and the imaginary parts, when you square the real, you have 1815, the word length doubles to 36, and the fraction length is the 15 plus the 15 is the 30. Of course, that's the same on the real and the imaginary. And then when you do that addition, you grow by one more bit. So again, we're seeing the same thing as the fixed point theory predicted as before. Also, what we're seeing is that the quantization error on the correlator output is 1.5 times 10 to the minus 5. And that's actually what we would expect. For 15 bits of fraction, we would have expected on this order of quantization error. So exactly as predicted. Now, when you go to the output of the magnitude squared, and I did put a little bit of a derivation in there, it's going to be a bit more. It should still be on the order of 10 to the minus 5, but keep in mind you're squaring something that already has a little bit of quantization error, so it would build up a bit. And I think it's a little bit out of the scope of today's discussion, but I did put in a little bit of explanation for that as well. And with that, I just kind of wanted to review kind of what we set out to talk about, and then in particular how we applied that in the final example. The idea was to really think about how to go from floating point mathematics to fixed point implementation that would do well on an FPGA, and to understand it from fixed point theory to the hardware concepts that come into play, and then how to express those in MathWorks tools. And if we look at what we did on that last example, we really kind of pulled it all together. So we started off with a matched filter that had to be implemented. We made sure that we quantized the input to an 18-bit word length, which is going to map well to an FPGA. We did the FIR itself full precision, so we don't expect there to be any mathematical error coming out of the FIR filter. We then quantized that output back to 18 bits. And we had a mathematical prediction for how much error we should get there, and we measured something that was exactly on that order using MATLAB and Simulink. And then we did the magnitude squared full precision, but we know there'll be a little bit of a buildup from the quantization error that we had here, and that was all measured kind of consistently. So again, for the design approach to go from floating point to fixed point, we set an input to 18-bit word length. We did the FIR full precision. We quantized only at that intermediate point as we went from the output of the FIR to the mag squared. Then we did the complex multiply at full precision, and then we measured the quantization errors.